Okay, welcome back. Let me see. Did you already send the links to the video files? So just in case you have to go somewhere or fell asleep, don't worry, you can watch the video later to fell asleep again. So today we will continue exactly where we ended up. So we ended here. So output status in B class. The A class was nice, but you can get only up to 25% of the 25% of efficiency, and basically this B class, or now we call AB class amplifiers, I think there is a promise for better. So basically, the first big problem with this B class amplifier was that there is across the zero signal, meaning the small signals, you have a lot of crossover distortion. Okay, but basically, if you make this biasing, you start a little bit of conducting of the current all the time, meaning, well, that's called a B class. So these very poor B class amplifiers you shouldn't use anywhere, so you should just have bias to make it as a B class amplifier. Okay, so there. So how to generate that bias? That's basically one classical alternative. So let's see if I need the need any of the blackboard now. So basically, okay, that's quite self-evident from this one already that the biasing can be done with the diodes. Okay, one diode has about the same drop in here as here, especially if you run a biasing with a current source. So basically that will shift the signal or the current biasing so that you get exactly 0-point match. Although this is a little bit tricky because you need to get, if I just draw this higher, upper part, so that's the biasing diode, okay, and then we have the basically the base current coming this way, keep it conductive, and that's the collector current, and that's basically the output current. And with the perfectly matched situation, load is here, the output is actually following the input if you have everything matched. Okay. But that basically is true only if you can match those properties. How you can match those properties? One way is to actually have a matched NPN pair so that you're using that part of the transistor here. That's a trick that dinosaurs used, ancient times. So that's actually just the base and emitter of a similar transistor. Right. So, yeah. So instead of diode, use a NPN transistor of that size, or with the same properties. Although, remember, this is now a high power transistor. I'm not sure if you want to put say, costly transistors there. Okay, but anyways, that'll work. That'll work just fine. Let's see. But actually, even better idea, just giving you some ideas here, is to basically put this one inside of a operational amplifier loop. Then basically you just need to have these two diodes there to make sure that there's not that much work for the operational amplifier to go over the crossover distortion. Whoops. Now it's messy. Now it's messy. Just a moment. A little bit better. Oh, by the way, I also noticed that a black suit is not good for the good for that white chalk. Okay, so fundamentally what you can do is to run this one from operational amplifier like that. Okay, and the only difference to the Monday's lecture is okay, so the crossover, basically, if you have, that's our desired. This is the input, and then the originally we have the required operational amplifier output here. But now, basically, due to that biasing diode, you drop it closer to that point. And same thing actually on the on the negative cycle. So now we have a nice linear operational amplifier driven AB class amplifier without virtually no crossover distortion. Okay. Although there are some small things like how to actually make a nice, good current source IBB there. But anyways, oops, let's see, plus VCC. That's also run from the plus VCC. Same thing here. And on this one biasing, see, this is open. You leave that one open. Okay. Good. Okay, maybe I should mark that A and B here. So that's point A, and this is point B. Good. And that'll work. That would work just fine. Okay, this is the same explanation there. Amplifiers, okay, if VI increases. Okay, so basically this has a limitation if you do it that way. So you have also that current source with limits, or basically this is also limiting. Let's see. Vmin. Where is the Vmin? Was it on the previous slide? No. Decreases to reach its maximum value. Okay, yeah. So basically, you cannot reach any more that high value. So On B-class amplifier, you can run it closer to the saturation or closer to the VCC. Here it saturates already a little bit lower volts, but that's fine. That is fine. Okay. Since we have a linear amplifier. Okay. Relationships of using biasing diodes. All right. Positive cycles. Q1 is on, Q2 is off. Yeah, output is about PC1. Okay. So this is basically just the calculus how these transistors are open. So positive cycles, this is conducting. So the I output is same as this current, because you have the upper part conducting, not the lower part. So basically that current is exactly IEE plus ICE1 but with a negligible amount of base current. Okay, and which means that output signal is simply, well, BCE1. Okay, so starting from here, there's that voltage drop, and this is the output signal. Okay, good. For negative cycles, the same thing, except you know that it's opposite signs. IC2 is drawn from that point, meaning I0 equals minus IC2. Yes, it looks fine. So we don't break the Kirchhoff's current law here. Good. But same way as here, you are only the collector emitter voltage away from the minus power supply voltage. And yeah, in output, of course, you have that relationship. That's nice, since that's Ohm's law. So we are not following those regulations on the given by physics here. Nice. Okay, that's important. When you're doing this kind of analysis, follow these Kirchhoff's laws of voltage drop, meaning the sign, and the same thing also follow the Kirchhoff's current law to make the make sure that you have the signs correctly. Okay. And usually you get problems when you have this negative voltage there. But basically, when you just take care of the to see which one is in principle the highest potential and start from there, then you should be basically on the right track. Okay. Wow. There's a load line without signal. Cut off, or Q1 and Q2 cut off is there at the same time. And basically this just states that the load line is very linear. There's no crossover distortion. Without the signal, we have perfectly balanced, so that basically we have a little bit of tiny bias current going through that way, but keeping this point at 0 voltage. And that you make by making sure that you have these diodes here match perfectly with the transistors. Okay, good. Okay, so what does it mean for the waveforms? Wow. So we have this nice output signal that follows the input signal, and output current is simply output voltage divided by the RL. What is this IM there? IM on the picture. IM, like Manolo. There. Yeah, that line. Oh, okay. Yeah. Oh, I see. It's there. Yeah. I see. Yes. Okay. So let's see. When you do the analysis for how much power you take, or actually how much current you take through the system. So basically, they have these three graphs. The first one is for load. That's what consumes power. Okay. So one, load. You have simply I out equals that one divided by the RL. That is also the input voltage, and that's if you have sinusoidal signal. V0 times sinus of omega t, okay? And if you do the math with that one, calculate the average power. Do we calculate the average power somewhere? Yes, we do. So basically, the peak current is simply the peak voltage divided by RL, as long as it does not saturate. Remember, we still have the saturation. It saturates at lower than the VCC. Okay, because also VCE and the bias circuit doesn't, let the base voltage to grow that high anymore. Okay, so load current is simply following the sinusoid. So that peak current is actually simply the peak voltage divided by RL. Yeah, nothing fancy about that one. It's a simple Ohm's law. Okay, and this is sinusoid. On the next page, we'll see how to calculate that one, but you should know if you have a sinusoid, you should now know how to calculate the power. Okay, on resistive load. The second one about the transistor Q1. The current there, it conducts only on the positive cycle. Like that. Contacts only on the positive cycle. Okay, which means that the mean square average of this signal is somewhere in here. So that's the IM. which you get when you calculate basically, that's the full cycle time t, but the signal is only on the first half cycle. So full cycle, but you integrate from 0 to half cycle. You don't integrate that one. And you have the I peak times sine omega t dt, and that gives you a value. And then the third part, Q2, which basically, well, let's see, that was that way. Okay. So it conducts only through the second half cycle. So this is a negative cycle, but positive value for that direction of current, this would be positive. Okay, and again we have the same the I peak, and also, well, if it's well matched, then you will have also the same mean current, root mean square current. Okay. Power balance. And each power supply actually provides that current of, well, 2 times VCC times IM. Okay, so on the positive cycle, it actually differs. In average, this current, and in negative cycle, it delivers on the negative side this current. So the current supply power. So how much the current the power supply is giving is 2 times VCC times IM. Okay, and with calculus done by Javi, we got 2 times VCC times the amplitude, signal amplitude, divided by pi times RL. Good. Any questions? You can do the math by yourself, right? You should be. You are engineers. You will be engineers. Let's put it this way. You can't be engineers before you can do that kind of calculations or find the source for it. I have a secret. So now professors actually say, okay, you shouldn't be Googling everything, since you should be able to, do the calculations like that. But when we were young and doing studies, we had this big book of tables that we could take a look at the all kind of formulas, including how to calculate the half cycle, the average current. Okay, that was the secret. So did you also have that kind of big tables? Yeah. Yes, that was good. That was our Google. It weighs about 2 kilos. Well, it's about the same as the laptops nowadays. Okay, nothing has changed really. Okay, then the average current on the load. So that's the load. And okay, so on the load side, so PL equals, so we have basically that. We can or should actually always do the calculations IL times BL dt, and there we have the sinusoidal signal on output, and this was just V0 divided by RL. So we are basically having 1 over T 0 to T V squared divided by RL times sinus squared of omega T dt, which gives you the magic divided by 2 there. All right, so we have V0 squared divided by 2 RL. Okay. Okay, efficiency of class AB. That's much power in, that much power on the load, and we have efficiency PL over PI is pi over 4 times V0 divided by VCC. And that actually has the maximum when we have about the close to the saturating signal. Okay, of course it will be. And then the efficiency will be pi divided by 4, which is more than 75%. So it's 78.5% efficiency compared to the A class 25 maximum. So it's 3 times more efficient circuit. So that's okay. 3 times better than A class. All right. And this circuit also, think of a no signal case. You have small bias signal or current here, just to keep this one, at 0 volts. You have some small currents here. So fundamentally, you don't have a big power consumption when it's turned off or in standby, basically. With 0 signal, this does not heat your house at the same time. It heats your house only when you start turning it on. And that's the big difference. So this is almost, green approach to the electronics. Almost. Okay, so how about the power dissipation in transistors? Okay, you have Q1, Q2. Well, both of those are only on the half cycle. So basically same PDQ there, and using the power balance calculations, the power supply power is consumed in load and 2 transistors. So remember, now we have a sinusoid signal, so that's it doesn't have positive or negative bias. So if you are running different waveforms, this will be totally different, of course. But for sinusoid or symmetrical waveforms, you consume the same amount of power in both transistors. Okay, so that gives you actually also formula for the as a function of minus V0 squared divided by 4RL. Okay, and that's a parabolic function of the input signal, and that's actually how it looks like. If we have VOC 0, then we have 0 voltage, yes. And then at the other end we have V0 is VCC, and we have the other end, and somewhere in between it has the maximum. And the maximum can be found, well, I told you already last week on Monday. So if you have this kind of parabola, again, see the sign here. That tells me that we have a parabola which is facing down, like that. And it starts from 0. Well, that's V0, V output. It starts from 0. Yes, put that 0 on that formula and you can immediately see that, okay, it starts from 0, so it must be like that. Okay, so we get the maximum efficiency at close to VCC. That's the maximum efficiency happens here. Okay, and that's the 78.5% of the maximum. Oh, let's see here. Yes, it's actually the same as the 75% of the maximum power, right? And, well, if you make a differential of that one with V0, you find that the maximum dissipation of the transistor happens on that point, which means that, okay, there when the V0 is 2 over pi times VCC, you have the maximum dissipation of transistor. Okay. Which is basically the maximum dissipation happens at the 50% efficiency. Okay. So when you're designing this system, you always design it for the worst case scenario. Okay, if you know that you have only sinusoidal signals, then you basically run for the worst case in average power. And that's the worst case in average power when this output signal is 2 over pi times VCC. Okay, so let's put it the other way. So what's out of a signal? So if we have a full tilt signal, it's a function of t. There you get the efficiency is about 78.5%, but if you drop into 2 over pi is about 70 some. If you drop this amplitude down there, then you have the maximum power dissipation of transistors. Okay, and you have the 50% efficiency of the circuit. Good. And then some summary. Summary. So from power supply point of view, let's see, maximum output power, meaning the maximum signal. Then you have the output signal close to the operation voltage, and you get that good, almost 80% efficiency. You draw, if you have the Pmax is the maximum power that you can consume on the load, then you basically have a power supply to give you 1.27 times the maximum power. So for 100 watts of output power, you need 127 watt power supply. Ha! Simple as that. Okay. Let's see. So if you get your hands on a standard, well, 10 years old PC power supply, that's 200 watts. So you could actually make that as a power supply for 150 watts AB class amplifier. That's a lot of noise. Although, well, yeah, a lot of noise. It's not designed for that purpose. Okay, and then of course it's designed mostly for 5 volts. Most of the current is on 5 volts. Okay, but anyways, and then the power dissipation on transistors is just on each of those. The maximum power dissipation on transistor is 0.135 times the Pmax. So for 100 watts output power, you're actually using just 13.5 watts in each of those transistors. Nice. You can live with that. You know, less than 20 watts is easily dissipated by just a small grid to keep it running below the breaking down temperature. And then maximum dissipation in the transistors for the highest transistor power consumption. So then, well, we are running it at only on at the say 0. So about 40% of the Pmax, meaning okay, our 100 watt amplifier would be then actually consuming 40.6 watts now on the load. So it's somewhere up, yeah, if you have from 0 to 10, that will probably happen at around 7 because of the logarithmic scale of the amplification. So around when you turn the knob to 7, that will be about 40 watts. When you play guitar. Okay. And you are consuming 20 watts on each of those transistors. Yeah, well, 40 watts on the loudspeaker 20 watts on each of those transistors, so 40 watts in total. So it's 50% efficiency, and then you actually are supplying it with 80%, 80 watts in this case, so 81.2% of the maximum output. So 100 watt amplifier at that point would be running at the power supply would be supplying 80 watts. Okay, that's nice. And okay, what is the average current? Yeah, it's that one. Wait a minute. Average current. In which case? 0 divided by pi. Oh, okay. Never mind. It's just a reminder. Never mind. So, good. And then there's a signal. And without signal, what happened without signal? What was the power in load? 0. And what was the power in transistors? 0. So what is the power in supply? 0. So it doesn't heat the room. Good. Let's take a quick look at what time it is, if it's a good time to take a time for a break. Let's continue a little bit since there is another. Is that the same one? Oh, compare with B class. Oh, yeah. So remember the yes. Compare with A class. Yeah, that there's a small mistake. Where you always have, we have this 100 watt amplifier now. You have 4 times 100 watts on power supply all the time. And then also the transistors, but this will generate the heat all the time, even when it's you are not playing. Okay, heat is on, and then of course the transistors are also heating all the time. Also the power supply is also heating all the time. Okay, so this would be probably a good place to, or actually, let's see, there's also design factors. Maybe we take that one. just trying to make it exactly a 1 hour. So designing power supplies. So basically, you need to take care on the power supply design that you can supply for the maximum power, actually also for the peak power. It must withstand the average power load at the maximum state. So for 100 watt amplifier, you need on AB class, you need that about 130 watt output for that the power supply. But you also need to take care of that the maximum peaks, how much current you take at the maximum from the power supply. Also the peak powers. And of course the voltage level. And then this amplifier itself, okay, you are dissipating on quite a lot of power there. So for 100 watts, you will taking actually at the worst case, you are running 20 watts on each transistor if it's sinusoid signal. Okay, still, if it's sinusoid. What happens if you are running this as a, say, voltage follower for a motor drive or something like that, and you run it constantly with that maximum power dissipation? Then it changes a little bit, right? So it doubles. Then in steady state, it doubles the power consumption on the transistor. So, but signals, yeah. And that's actually one reason why on audio amplifiers, although this is ugly since it does bad things to your signal, you usually bias it to 0 and then have a high pass filter at low signal, say cutoff frequency at around, say, less than 20 hertz. So that's what you do for the audio amplifiers. You never DC couple of audio amplifier, otherwise you end up, killing the amplifier if you have a DC signal coming in. Okay. So, yeah, we will use the calculation estimations of the theoretical analysis. Okay, so that was our theoretical analysis. Okay, now for that 100-watt amplifier, I would also include here some engineering factor. So you design in exactly 127-watt power supply wouldn't do much good. You need to actually multiply it with some safety marginal, because you probably are consuming a little bit more power there. Okay. Then also that 20 watts power consumption on amplifier, that's good only for the sinusoidal signals. How about if you are saturating your signal? It's, well, how many of you are playing electric guitar? Nobody. What? You will be engineers. Okay. What is the difference between the signal from a normal guitar and a heavy metal guitar? You know the difference, but you can hear the difference. What happens there? That's the distortion. What happens on the heavy metal? Because Jimi Hendrix overdrove the amplifier status so that it actually you get clipping distortion. Meaning, okay, you try to drive it like that, but your power supply is like this. So that's actually what you get out. Okay, and now think of the difference between the sinusoid with the same maximum amplitude and this almost, this square wave signal input. This one has more power on it. You need also more power everywhere there. This is better, More is better. So basically, for audio amplifier design, you are not just taking this sinusoid signal as your the worst case scenario signal. You are taking this one as your worst case signal. All right, and then of course, let's see. The worst case happens when you are saturating this one on that highest power dissipation on your transistor. So, meaning you are overdriving the pre-amplifier states, not the power amplifier. You overdrive the pre-amplifier state, meaning that this actually becomes square wave. Ooh. Yep, that's when you get into deep trouble if you design it only with this, theory based on sinusoidal signals. So engineering factor of 2 is okay. Okay. Good. Other factors? Saturation limits, yes. How close to the VCC you can actually reach. And yes, that's a good design. Good also to avoid destruction of the output transistors. So there are these limits on datasheet. The maximum current limit. Yeah, the transistor must be able to run the basically the highest current possible required by this load. And on say normal signals, it means short circuit from power supply to this one. That's the absolute maximum. What comes here as a constant current, but okay. Audio amplifier. It's not that simple as that, because it's actually that element has also some inductance and also some capacitance. So the peak current can be anything else. So it can be, several times higher than this average current. So IC max, yes, take a look at the IC max, but take also note if that is the peak IC or is that a IC max in average. Both of these parameters are actually given usually. Okay. Then of course the current you need to take care of that. It's it has enough of the current amplification beta. Yeah. If you don't have enough of power current amplification, you may end up having the worst case scenario by accident. So running with the highest the design efficiency might actually end up being running it at lower current, meaning the higher power dissipation on transistor. Okay, then of course the maximum voltage difference from here to here. Okay, remember when you're running this near to saturation, this signal goes to close to minus VCC. Okay, which is also the increasing that minus VCE here. Yeah, see, just mark it in the minus VCC. What is the VCE here when you have negative signal? Okay. So that's one design consideration. So if that was, say, 20 volts plus 20 volts, then you have minus 20 volts. The maximum, so this transistor VCE should withstand 40 volts of the voltage. Okay, and of course that PD max. And to be on the safe side, think of the worst case, what can happen. You know the Murphy's law. Bad things happen. Bad things happen when you least expect it. And when bad things happen, it's the worst case scenario. And that's that way. Okay. And yes, fast or slow signals All right, on slow signals, it means that you will be going in the steady state situation. If it's fast, then you can work with the average powers. But if you are actually slow signal, then this the transistors have some time to heat up. Okay. Short circuits, yes, that can happen easily. The user takes instead of a loudspeaker, a user takes just a wire and plugs it there. Or sometimes actually, when you have too small loudspeaker, you melt the insulation in between the coils, and then it becomes a short circuit. So the amplifier shouldn't break if the user or the next stage breaks down. All right, and that kind of things. Okay, that's a good place to have a break. Okay, 5 minutes. Sure, no problem.